Swayam Prabha. Digital India. Educated India.
Welcome to lecture number 3 in this NPTEL online certification course on bioreactors, a 10-hour course. In the first 2 lectures, we got introduced to what bioreactors were, what kind of products they make, what are the common types of bioreactors that are used, what are the modes of operation, predominantly batch, continuous, and semi-batch or fed batch, and then we started looking at some details. The first aspect that we looked at was how to have a clean slate, because we said we kill all organisms that are there, we create a clean slate, and then we introduce the organisms of our interest into the bioreactor, which produces the product of interest to us. To achieve the clean slate, there are 3 methods possible, 3 main methods possible: temperature based or chemicals based, chemical vapors and so on, or radiation based, gamma, UV and things like that. Then we saw thermal sterilization, the temperature based aspect, in some detail, so that we had enough information to be able to design a priori the sterilization process. That's the whole point about analyzing and so on. It also gives us a lot of insights, but the practical aspect is to be able to design appropriate processes. Let me open this particular presentation. This is what we saw, the thermal sterilization, the response of viable cells to high temperature. We have on the y-axis the percent viable cell concentration on a log scale versus time on the x-axis, and the relationship is linear when this is on a log scale. Also, we said that the slope of the decrease increases as the temperature increases. This is the kind of response that we were trying to analyze. We said that we could analyze this situation if we considered the rate of decrease in concentration to be directly proportional to the concentration of viable cells, a sort of a first order relationship. Using that and the fact that this operation is happening in a batch bioreactor, we wrote a balance for it and arrived at let me get there. This was the governing equation. d dt of xv is minus kd into xv, and if we solve this, we would get ln of xv naught by xv equals kd t. That gives you the time there. The time needed for the viable cell concentration to go down to xv, starting from xv naught, is 2.303 by kd log to the base 10 xv naught by xv. As you can realize, this is natural log to the base e. When we convert that to log to the base 10, you have a factor of 2.303, but otherwise this is essentially this equation transposed. The main thing here is that we have the time that is necessary for the viable cell concentration to go down from xv naught to xv under certain set of conditions, which is characterized by this death constant kd, or the sterilization constant kd. So this is what we arrived at, and then we also looked at something called a decimal reduction rate, which is the time that is required for a 10-fold decrease in viable cell concentration at a given temperature. For a 10-fold reduction, all we needed to do was replace xv naught by xv to be 10, and then we got the decimal reduction time d as 2.303 by kd. At this point, a problem was assigned. The practice problem 1.1. It read, a bioreactor needs to be sterilized before use. The solution in the bioreactor consists of single cells with similar thermal response characteristics. At 70 degrees C, it takes 5 minutes for the viable cell concentration to reduce to 20% of its original value. A, determine the decimal reduction time, and B, how long would it take for the viable cell concentration to reduce to 0.1% of its original value under the same conditions. This was the question that was, or the problem that was assigned when we pretty much finished up the previous lecture, lecture number 2. I hope you had a chance to work this out. I will, as promised earlier, work out problems that are assigned in the beginning of the next lecture. We will start this lecture by solving this problem first. Let me first talk a little bit about problem solving. Problem solving is a higher level skill. It's the same way as somebody being able to either sing well or dance well or play a game well, or come what may, you think of skills and you have a certain association with it. Similarly, problem solving is also a skill. In fact, it's a higher level skill in the cognitive domain. Some people would be naturally good at it, as are some people who have a natural ability in music, in dance, and so on and so forth. If you have the natural ability, then this initial part or the details of the problem solving may not be very necessary for you. You're already at a good level. I think you should continue with whatever you're doing, do the problems that are assigned, and you should be fine. However, in my experience, I've found that most people do not have problem solving as their natural skill. It is necessary for us to pick up that skill because it is necessary for this profession. And if you don't have a natural skill but you need to do something, then you need to pick it up. To pick it up, of course, we practice, we put in effort, and then we get to a certain level of being able to do problems. I'm sure with consistent good effort, you would be able to solve problems. We will limit ourselves to what are called closed-ended problems in this course. Closed-ended problems are problems in which everything that is needed for the solution of the problem is either given in the problem statement or is known through material in your notes and so on and so forth. This is distinct from open-ended problems that may not have all the information that is required stated in the problem or known. You might need to extend a few things and then get information from other sources, literature and so on, and then solve the problem. In fact, in my regular courses, I do assign a semester-long open-ended problem to be solved over the entire length of the semester. That's a very good learning experience for the students. This format does not allow us to do that effectively. So let us at least look at closed-ended problem solving for this course. If you are interested in knowing or in developing the problem solving skill in a systematic fashion, you may want to look at this book. This is the title of the book is Strategies for Creative Problem Solving. The authors are Scott Fogler and Stephen LeBlanc. It's a good book. You might want to take a look at that book if you want to know a little more about problem solving, if you really want to get into it and become an expert with sustained effort. With that, let me go on to how we are going to go about closed-ended problem solving. The first question to ask is, what is needed? What does the problem want us to find? Once that is clear, write it down. Then ask the question, what is given or known through the problem, through the material that is relevant to the problem that was covered in the lectures, and so on. Once both those are clear, then we will ask the question, how do we connect the first one with the second one? How do we connect the needs of this particular problem with the givens or knowns in this problem? And while doing that, we will also ask, are there any basic principles that we can rely on to be able to solve this problem? In fact, while presenting the solution, I am going to use only the first three: what is needed, what is given or known, how do we connect the needs with the givens and knowns, and take this as a part of the third aspect. That's how I am going to do it. Now, let us go about solving the problem that is posed. We have already read this. We need to find the decimal reduction time in part A, and in part B, how long would it take for the viable cell concentration to reduce to 0.1% of its original value. Some information is given. The solution in the bioreactor consists of single cells with similar thermal response characteristics. Therefore, you can assume linear dependence of the log of the viable cell concentration with time, as we saw in class, saw in the lecture. And also it says that at 70 degrees C, it takes 5 minutes for the viable cell concentration to reduce to 20% of its original value. Okay, having seen this, let us go about the solution. First question, as we said, was what is needed. Let us take one part after another. Part A, the decimal reduction time. So that is clear. So let us ask the second question. What is known or given? We know that it is a single cell suspension. We discussed this earlier too. And also we know that at 70 degrees C, it takes 5 minutes or 300 seconds for the viable cell concentration to go from 100% to 20%, or in other words, a 5-fold reduction takes the 300 seconds. Please see that I have converted this 5 minutes into 300 seconds. Okay. It is usually good to work in a consistent system of units, whatever that might be. And for the purposes of this course, we will mostly use the SI units. And that's the reason why I have converted 5 minutes to 300 seconds. It is good to do this a priori and then go about the actual solution, or beforehand and go about the actual solution. Then the third main question, how to connect what is needed to what is given. If you think about it, I'm sure quite a lot of you would have solved this. If you think about it, we have derived the decimal reduction time, which we also reviewed a few minutes ago, as 2.303 by Kd. Therefore, we need Kd. If we have Kd, we can find out D, which is the decimal reduction time, which is what is required in part A. How do we find Kd? To do that, let us go back and look at the basis for the derivation of decimal reduction time. I think we went through it during the review process. So let me just say, this gives the time for the reduction in viable cell concentration from xv0 to xv. We had derived the time to be 2.303 by Kd log to the base 10 xv0 by xv. We have the information on the time taken for xv0 by xv to be 5, or in other words, a 5-fold reduction from 100% to 20%. So that if we substitute here, in other words, this becomes 5, right? So we need 5 minutes or 300 seconds for a 5-fold reduction. Therefore, 300 equals 2.303 by Kd log 5 to the base 10. So Kd is the only variable here, and Kd, if we transpose this or essentially multiply both sides of the equation, you can do the same things to both sides of the equation that you know. If we multiply this side by Kd and this side also by Kd, we get and divide this side by 300 and this side also by 300, we get Kd equals 2.303 by 300 log 5 to the base 10, which turns out to be 5.37 into 10 power minus 3 second inverse. I would like you to verify this particular answer. If you have this answer, fine, but please verify. I have deliberately not verified my answers during the solution process alone. I've done that for the exam questions and so on, but during the demonstration of the solutions of the problems, the practice problems that are assigned, I have deliberately not verified my answers. If you find an error, please point it out. That will be a nice exercise for you. Now that we have Kd, we can find the decimal reduction time as 2.303 by Kd, which turns out to be 2.303 by 5.37 into 10 power minus 3, or 428.9 seconds. Because this was in second inverse, we get this in seconds. If you divide this by 60, we get 7.2 minutes. Okay. Therefore, it takes 7.2 minutes for a tenfold reduction in the viable cell concentration under these conditions. Now, let us consider part B. Again, we'll ask the same questions. What is needed? The time taken for the viable cell concentration to reduce to 0.1% of its original value under the same conditions. What is known or given? Single cell suspension, the same as earlier. At 70 degrees C, it takes 300 seconds for the viable cell concentration to go from 100% to 20%. And also we found in part A the value of Kd and the value of the decimal reduction time. This is what is known. How do we connect what is known to what is given? The time for reduction in viable cell concentration from xv0 to xv, we have already derived and seen earlier also, that equals 2.303 by Kd log to the base 10 of xv0 by xv. When the viable cell concentration reduces to 0.1% of its original value, this is the condition that is of interest to us in problem B. We know that xv by xv by xv0 is 0.1. If xv by xv0 is 0.1%, this is percent. If we convert it into fraction, this will turn out to be 0.1 by 100. Percentage is always out of 100. So fraction is, when we need the fraction, we need to divide it by 100. This is 0.001 or 10 power minus 3. So xv0 by xv, if we flip it around, it will be 1 by 10 power minus 3 or 10 power 3. And thus the time required for the viable cell concentration to reduce to 0.1% of its original value would be just substitution of the various known aspects now into this equation. 2.303 by 5.37 to 10 power minus 3 log to the base 10 of 10 power 3. That turns out to be 1286.6 seconds or 21.4 minutes. This is one way to solve the problem. I have shown you all these steps. Hopefully you understood these steps, and if you be at it, if it's not natural to you and if you be at it, I'm sure you'll be able to solve closed-ended problems. I think we will finish up lecture 3 with this. These lectures would be of variable times. They'll all add up to around 10 hours. Each lecture would be of variable time. We will meet in the next lecture, lecture 4. See you then.